Hello, everyone, and thank you all for joining us. The views, opinions, technical analysis presented during this webinar are those of Evonik and not necessarily those of UL. The appearance of this content on UL sites does not constitute an endorsement by UL or its affiliates. Today's webinar is VESTAMIN A95, Specialty Building Block for Polyurethane Dispersions PUD Manufacturing, and is presented by Evonik. Your presenter today is Guido Stroikens. Guido is the Director of Applied Technology for the product line VESTAMIN A at Crosslinkers. He is a chemist by training and has been with Evonik since 2007. My name is Abby Puro with UL, and I'll be moderating today's event. Please send us your questions by typing them in the question tab located on your screen. We are recording today's event, and we'll send you a link by email when it's been posted to ulprospector.com. Now, I'd like to turn the presentation over to Guido. Would you like to begin?
Yes, thank you very much for the introduction. Good morning or good afternoon to the guys who are sitting in Europe as I am today. Welcome from my side. I'm going to talk a little bit about one specialty building block we're offering, the VESTAMIN A95, which is mainly used for PUD synthesis. Before that, I want to apologize. Other than in the invitation, it is not Dennis Pokrop presenting today. He was not available on very short notice, so I hope I can step in appropriately. Let's see where we get. To start, I would just briefly want to introduce our business line in a couple of words. So business line Crosslinkers. We're proud to be pioneer of the so-called isophorone chemistry. As a matter of fact, we're celebrating 60 years of this isophorone chemistry this year. And it's a long time and still very vivid products. What are these products? If you just have a brief look at this so-called isophorone chain, we start with acetone and we make the so-called isophorone, a specialty solvent you see here in the middle left. And then we further derivatize these isophorone to the IPD, so isophorone diamine. So IPD is one of the diamines or the main diamine we produce, and then these diamines we also turn into diisocyanate, and this is of course in the I chain, the isophorone chain, the IPDI. So our I chain is the core of the whole business line, I would say, not the only chemistry we do, but we mainly stick to producing diamines and diisocyanates. That means we are making raw materials, we are making crosslinkers, as the name of the business line tells you, for diamines for epoxy curing and diisocyanates for the curing as hardeners for polyurethane chemistry. And that, of course, goes into several different applications. We have many applications in automotive, so polyurethanes can be employed as elastomers, TPUs, but also, of course, exterior coatings. The isophorone itself is mainly used in solvents, but also synthesis building blocks for things like, for instance, vitamin E. Then we have a huge field of polyurethane powder coatings we're serving. And on the right-hand side, we have composites. This is, of course, mainly driven by the epoxy business. Different kinds of industrial coatings, of course, many polyurethane applications go into wood, go into flooring, but also, and this is the lower right, what we want to talk about mainly today, the polyurethane dispersions. So when we think of polyurethane coatings, maybe as we see here on the top left on an automotive body panel, on metal, or it could be wood, as we see on this bowling alley. But we can also think of daily things like cans for food packaging. Also, they are coated with polyurethane coatings, actually on the inside and on the outside. Or as we see here on the lower right, we see window frames that are made of metal, and they are coated in a special, let's say, way that they have the appearance of being a wood window frame. All of these have in common that they're made of polyurethane, and usually when we think of these polyurethane coatings, we're thinking of cross-linked systems. That means we have, in a very simplified picture, we have a resin called A here, and we have some kind of crosslinker called B, which then reacts to a three-dimensionally cross-linked network, right? So that means we have a reactive system, and it can be in many cases 2K, where you have to pre-mix them right before the application, but it can also be 1K when you think of blocked reagents, that you have heat cure systems that are served and stored in a one component way. But all of them have in common that you need, after the application of your coating, you need some chemical curing, some cross-linking to take place, right after the application. But it is relatively unique to polyurethanes that they also make for excellent coating systems if you don't have any additional cross-linking, right? So if you have very long polyurethane chains, polymer chains made of polyurethane that are just thermoplastic and are not cross-linked, they form these these interlinkages, like these hydrogen bonds, that cause these relatively good and decent properties, even if they are not truly three-dimensionally cross-linked by, let's say, typical chemical bonds. So that means we can make thermoplastic polyurethanes and have them applied as a coating, and then just apply them and don't cross-link them anymore, don't have a curing mechanism anymore. That means after the application, we only need physical drying, right? Many of these coatings, many of these systems work very fine, but we have, of course, then to take into account that we need relatively high molecular weights of these polyurethane chains that this system works, and that these properties, the chemical resistance, mechanical resistance, etc., stay on an acceptable level. And in order to get these relatively long molecular weight chains dissolved in an appropriate solvent, we either get very high viscosities, or we get very low solid contents. We have to very, very far dilute these systems that they stay on an acceptable level viscosity-wise. So you have to choose either high viscosity or low solid content. And this is actually where, at this point, then come the dispersions into play, right? The polyurethane dispersions are chemically exactly what we saw in the picture before. That means we are talking about thermoplastic, uncross-linked polyurethane chains, but now they are not dissolved in an organic solvent anymore. Now they are dispersed in water. Dispersed means they have nanometer-sized nanometer-sized particles finely dispersed stably in water. We can imagine this, I think, mostly like milk. Also there we have the fat particles finely dispersed in water. And so now when we have this dispersion, now the viscosity is not depending on the molecular weight anymore. It is now only depending on the particle size. So that means the original development goal of polyurethane dispersions was just to ease the handling of my thermoplastic polyurethanes that came out of the solvent world, transferred into water to make it easier to handle, get higher solids, get no problems with viscosity. But obviously today, with stricter emissions regulations and VOC limitations, etc., of course, being waterborne has also a much more important maybe advantage nowadays than it had in the past. So polyurethane dispersions are becoming more and more important even nowadays. But of course, as you can imagine, having such a purely organic hydrophobic polyurethane as a chain, to have this stably dispersed in water, is not straightforward to synthesize. And this is actually what we want to talk about a little bit closer today. Typical applications are not only limited to coatings. We see on the far left, of course, a typical application. Car body is a typical application. Most of the base coats, or the color giving base coats of automotive OEMs, are meanwhile waterborne, are PUD based. They are then protected by a classical cross-linked system, the clear coat. We have several wooden applications. It can be wooden floorings, it can be wooden furniture, or the like. But also, if we go into the middle, we can not only go for coatings, we can also go for adhesive layers, right? So this is an adhesive for wooden flooring. Also, this can be made of PUDs. Another interesting field, which is also gaining more and more interest over the past, let's say, I don't know, 5 years maybe, especially in Asia, especially in China, is the manufacture of artificial leather. So PUDs have been used already in the past quite extensively for the final protective coating of both artificial leather and genuine leather. But the actual production of polyurethane-based artificial leather, so the body of the artificial leather, that usually was a solvent-borne process in the past and is now also, due to stricter emission control, stricter regulations, turning more and more to waterborne, turning more and more to PUD. So how do we now synthesize such a PUD? And I want to now emphasize on one particular process. Of course, there are some alternatives, but we think the acetone process we want to show here is the most widely used nowadays. And we start here with the so-called NCO terminated prepolymer. That means we start with an OH functional resin, the diol, and we react this with the appropriate isocyanate to form these molecules we see in the right box, so that we have the ideal case that we have actually one resin molecule react exactly with two isocyanate groups, and you carry out this synthesis in acetone in a low boiling solvent. We will see later on why this is the case. In many cases, I would say the diisocyanate of choice you use here is the IPDI we have just introduced in the isophorone chain, but you can also use other isocyanates. For instance, we have here another one, which is the H12MDI. And the difference in between these isocyanates is their selectivity. IPDI has two differently reactive NCO groups, so you can very easily achieve this ideal picture of the 2-to-1 ideal stoichiometry of your prepolymers, whereas when you have an unselective isocyanate like the H12MDI, you get more and more chain elongation, which then increases your viscosity. So this is an unwanted reaction. You don't want to emphasize on the chain elongation for this viscosity reason. And of course, if you have more chain elongation, also you will have unreacted monomers, and having unreacted on the unreacted monomers, which give you problems with toxicity, of course, of your prepolymer. So both effects want to be avoided, and that's the reason why you want to go for the above picture, where you have the most selective synthesis possible. Then, of course, when we want to later on bring our polymer into water and disperse it into water, we have to make it more hydrophilic. And this is why we have to add some emulsifier to the prepolymer. The most commonly used emulsifier nowadays, I would say, is the DMPA, dimethylpropionic acid, which is both an acid, has an acid function where we incorporate the hydrophilicity into the system, and we have a diol. So that means the diol function acts kind of a resin. It's a very short diol. It's not a long chain resin. So we can see here on the in this schematic picture on the lower right, we have a very short chain, which then also can react with the isocyanate. So it's built into the polymer, and the side chain of the acid sticks out on the side. This acid, of course, to be later on stable and pH neutral, needs to be neutralized, and for this we take we usually take amines. In the most simple one, or the most commonly used, I would say, is triethanol amine, TEA. This is then later on added. This is not now just to neutralize the acid and to also cause the acid to turn into a salt, and this salt has then even a higher hydrophilicity than the acid would have on its own. So now we come to the what I call the steps 4 and 5. We always would mention them together, and it's literature debates if you do number 4, the addition of water, and the chain extension, which one you do first, or do you do it simultaneously. For sure, you have to do it in, let's say, a timely manner, close together. So now what we want to do is we bring our pretty polymers together, we link them together with the chain extension to a long chain, and at the same time, ideally, you want to bring them into the water that they can, bring the smallest possible particles that they get, that you get the most stable dispersion. If you do the chain extension too early and then you wait forever, your molecular weight will build up to very, very high dimensions and you cannot disperse it anymore. So it's a bad idea to start with number 5 and then forget about the water. On the other way around, when you just add the water and forget about the chain extension, well, the water will attack your isocyanate groups and decompose the isocyanate. So it is really important that you have both steps in mind together. The reason of this competing, or the reason, that the water attacks your isocyanates and the isocyanates are then decomposed is the reason that we use as chain extender usually also diamines, because diamines react very, very fast with isocyanates, much faster than water would do, and also much faster than another diol would do. So that's the reason why we here take advantage of simple diamines that are very, very reactive towards isocyanate groups. So the simplest one imaginable is here the EDA, the ethynyl diamine. Also other amines are thinkable. Basically any diamine you can think of works, but in most cases literature describes the EDA. In the middle, I have pictured, the final picture of my schematic chain. So it consists of the longer chain prepolymers, it consists of the shorter chain prepolymers, it consists also of the side chains of with the hydrophilic groups. But when you go lower to this scribble, should just envision that, or picture, that if you have then finally your particle on water, your organic, your hydrophobic parts will stick to the inside, and the hydrophilic groups, they will stick to the outside, and they will then cause this stability of the particle in the water, so that actually by this hydrophilic groups sticking to the outside, you kind of physically hide the organic hydrophobic groups from the water. So and then of course, this is an optional step. Some people do it without, some people do it with. So if you want to have a pure waterborne system, which has no VOCs, you have to make sure that you can now get rid of the acetone. The PUD technically also works without doing that, but nowadays we want to have pure waterborne systems. So that means we evaporate the acetone. Here we apply usually just limited amount of heat, moderate temperatures. This is good for the stability of your particles, that you cannot or do not heat it up too much. And then you apply vacuum to just evaporate the acetone. And that is the reason why we chose the acetone in the first place, because it is relatively easy to remove via distillation or via evaporation. So when we look at this process, it has some downsides on the handling of this whole synthesis process. First one to mention is the DMPA, our acid. Our emulsifier is a solid, and it's a hydrophilic solid. I mean, that's its role, right? So the dissolving in the acetone in the organic phase takes very long, and we have, due to the fact that we use acetone, we have relatively low temperatures. We cannot heat it up to speed up the dissolving process. So here you lose often several hours in dissolving only the DMPA. Second is that the hydrophilicity of the DMPA is rather limited, so you need relatively high amounts to obtain the desired amount of hydrophilicity, so that you also get decent solid contents and in your dispersion. So both are factors of the DMPA where we think this is not the ideal solution, and this is where we want to present you the alternative. We call it VESTAMIN A95. This is a combined emulsifier, so it has also hydrophilic groups. In this case, it's a sulfonic acid salt, and it is combined with a chain extender, so it is also a diamine. So it is emulsifier and chain extender in the same molecule. One big advantage is it is provided already as a 50% solution in water, so you don't have this lengthy dissolving step anymore. You have an increased hydrophilicity, so that means the sulfonic acid salt is more hydrophilic than the DMPA or the DMPA salt. So that means you need either less of this material in your formulation or you achieve higher solid contents. So up to you which way you want to choose to take advantage of the system. If you now have a look at how the whole synthesis process changes, of course, we first synthesize again the prepolymer, especially with our long chain particle parts, right, with the long resins. We have no changes there. We can choose, of course, to add here pictured on in the picture block with the Y part. We can choose to add other short chain building blocks because we now don't have the short chain DMPA anymore. And now we have another chain extender, again, then pictured in green as in the last pictures, that is now carrying your hydrophilic group. You can use the A95 as chain extender alone. You can also combine it with the EDA, the classical diamines, if you choose to use less A95 also. This is an option. So you have basically way more design freedom because you need less of this molecule and you can combine it with long chains, short chains, prepolymers. You can combine it with other amines for chain extension. Everything is up to you. And the last part, as I said also on the last slide, no dissolving is needed. So other than the DMPA, we have a directly liquid to start from in your synthesis. So, and then of course, after this chain extension, we add the water again. Here is no change in the process. And also, of course, the evaporation of the acetone. Also, this needs to be done in this case. So also, yeah, no big changes to your synthesis process in this case. Just as a summary again, what is the main advantages of this system or this molecule to be used in the synthesis? As said, we have the full design freedom, so we can, since we need much less, so we are less dependent on one molecule in our formulations, and we can then build up the other building blocks way more freely. We have lower process time because we do not have this lengthy dissolving step. We can achieve higher solid contents, and we have overall a less complex process. This is now the synthesis part of your PUD. How does this all now affect in the performance of the PUD? That's maybe also the deciding factor. Is it performing as well as a classical PUD? Is it even better? That's why we have prepared a comparative study of some, let's say, prototype PUDs that were aiming at just being different in this one particular point that we just changed the emulsifier. So we wanted to really have the exact same formulation. So as you see here with the prepolymers here in this table, we in both cases have taken the same long chain building block, which is an oxyester. We call it it's a polyester with a molecular weight around 1000. We have another short chain building block, the 1,4-butanediol, both with the exactly same equivalents. We have some TMP in there for some branching of the PUD. And then the big difference is then that we use in the prepolymer A, which is DMPA based, we use 3 equivalents of the DMPA. And we exchange that in the A95 based prepolymer. We exchange this with neopentyl glycol, which is having the same molecular weight as the DMPA. So we have to exchange for this short chain DMPA building block we are using in the prepolymer. We chose the NPG, which is as close as it can get just without the hydrophilic side group. The isocyanate is in both cases IPDI, and in both cases we perform the synthesis in acetone 30%. What do we do with these prepolymers? The first step, and this is a difference, we have to admit the dispersion, which is based on A95, gets some additional acetone, so we need some more acetone in this case. This is maybe this additional step is then compensated that the DMPA-based system needs to be neutralized, as we discussed. This can be skipped, of course, in the case of A95. We already have the salt. We don't start with the acid. The chain extension is done on the left-hand side with pure EDA. On the right-hand side, as I said, we don't need to rely purely on A95. We can also combine it with EDA or other diamines. In this case, we have a very, very high content of A95, so it's used 15:1 with the EDA, so almost pure A95. So even with this unoptimized, just let's say, taken the existing dispersion A, which is DMPA based, and just stay as close to this formulation as possible, just exchanging it with the A95, we are able to increase the solid content from 33% solid to 42% solid. So you increase your solid content by roughly 1/3 already. How does this now perform? We have here on the left 2 bars, we see the solid contents, again 33% solid versus 42. The process time in this case saved us 2 hours of the, mainly the dissolving step of the DMPA. In the middle 3 bars, we have some mechanics. So here we also see that I would say, both are convincing, both are perfectly fine. We have Ericsson coupling of 7 millimeters. We have a slight difference in the ball impact, but I would not overestimate this difference. Maybe I would say the difference and the advantage for the A95 looks bigger than it is. Actually, those those values are pretty comparable. Also, the pendulum hardness after 7 days, 150, 140, very close together. In this particular case, we have even for the A95 a higher chemical resistance in terms of MEK and ethanol double rubs. So roughly 100 to 150 or 60 to 150. But also here, I would not overestimate this advantage. This can be compensated if you if you tune other parts of the formulation. So I would say, again, they are pretty close together, DMPA and A95. What we have to admit, of course, at this point, and we cannot avoid it, or we should mention it in any case, the water resistance of the A95 is significantly lowered. If you use a system that has a high content of A95 and you choose to go for high solids, you will have a reduced water resistance of your dispersion. So the question is then, as I said, we have not yet optimized this system or, tuned this system to A95. We just took the polymer as it came and just exchanged the A95. Can we now go even to higher solids? Well, we say when we stay with this, let's say, relatively hard formulation, you remember we had very high amounts of hard components and we had a relatively short 1000 molecular weight polyester. The solid content is already at the limit, as we would say, but if you go for higher solid contents, you just increase the amount of flexible backbones. So we go, in this case, for a poly THF with a 2000 grams per mole molecular weight, exchange this, exchange the polyester we used before in the first examples. We now choose this poly THF 2000. So you see this in the table, right? So you have now a pre-polymer C, which is again in most of the properties unchanged, except for the polyester is not used anymore. Now we use a doubled molecular weight poly THF based. For the rest, we did not change anything again. And when we now compare this in the same bar or bar graph as before, we see we can now even go to way higher solids. We can achieve now 55% solids. So an additional increase. The process time suffers because now we are, with this very high solid contents, we are facing also increased viscosities. So the high viscosity during synthesis time brings you back in process time a little. The cupping and ball impact, of course, are very fine. Again, these are reflecting your flexibility. Of course, this is convincing, right? If you choose a more flexible building block, you should not expect to suffer in the flexibility, but the pendulum hardness, of course, this goes down. If you choose to go for high flexible molecules, this is also not surprising. We are mechanical property-wise, we are very close again to the original DMPA status. So I would say it's still okay, just a little bit lower than with the original 1000 polyester. And again, we used a very high amount of A95 to get the highest amount of solids possible. So we have to admit again, we did not save the water resistance, which we could not be expected, of course, but just by changing the resin. So when we now talk about properties and how to influence, final question: what is now does have the bigger influence? Your emulsifier or your polyol? And this is one thing I really want to point out, right? When we take, this is now another formulation, not really directly comparable with the examples you saw in the last slide. We now have a purely soft formulation, no hard segments at all anymore. And we take this polyester we talked about earlier with the molecular weight around 1000. We have relatively poor resistance both in the DMPA and the A95 case, even a little bit lower with the A95. Yeah, the resistance against certain chemicals, sodium hydroxide solution, double rubs with ethanol, and double rubs with MEK. So they survive not very many of these double rubs. If you choose this, yeah, without any hard segments, very soft PUD. If you now just exchange again the resin and don't do anything else, you'll see that the impact of your resin is way, way, way higher, right? So here you can improve drastically your resistance in both cases. And the effect of your polyester and your building blocks basically here is way, way higher than it would be just by exchanging the emulsifier. So that means by taking advantage of the, let's say, the advantages the synthesis gives you for the A95 and the higher solids you can achieve with the A95, if you suffer at all in your properties, you can easily overcome this usually by just fine-tuning the rest of your formulation with your diol building blocks. Just tweaking them a little should overcompensate all other properties that are induced by exchanging the emulsifier DMPA to A95. I think this is already the final picture of the presentation. So just at a glance, again, when we start from the lower left with number one, we have a much easier process in our eyes. With the A95, you have shorter processing times, and you can also tune your formulation more freely. You have more design freedom. We have a more efficient application of the PUD at the end customer, so you have much higher solid contents, which allows for a more efficient, of course, packaging and transport of your PUD, but also after the application, your drying is also much more efficient since you have much less water that needs to be evaporated. The chemical resistance and also mechanics are on a similar level as the state-of-the-art systems, and due to your high degree of design freedom, you can easily further tune them. We have to admit that the water resistance, this is an issue. So long-term water exposure, I mean, this is, I would say, common to all PUDs if they're not further cross-linked, right? So hydrophilic PUDs are usually not very stable to water, but in this case, the stability towards water is even less. So that means the long-term water exposure should be avoided. So for instance, certain applications like adhesive, they don't come into contact later on when you have your layers glued together. They don't come into contact with water at all. Or you have automotive base coats where you have a protective layer of your clear coat on top. Also there, water is, for instance, no issue. So there's a lot of applications thinkable. Also the artificial leather usually is coated with a protective layer again. So there's a lot of application thinkable, but this is not a problem at all. And also can be overcome by other means. So yeah, these are the main points about A95. And if you have any questions, just let me know, or we will, I think, pick them from the chat. And I'll hand over back to Abby.
Hello, everyone. We'll try to get through as many questions as we can, so please remember to put your questions in the question tab located on your screen, and we'll go ahead and get started with Q&A. So our first question is, Why do we need extra acetone in the process when using A95?
Okay. So the I can go back. Yeah, we had some. This is the point where we were talking about. So we need extra acetone. In this case, because we do the chain extension before we actually add the water, right? When we talked about the classical system, I pointed out that you that you want to do the chain extension and the water addition as closely together as possible. In this case, with the A95, we do actually the chain extension and adding the emulsifier at the same point, right? When you use the DMPA-based method, you add the emulsifier right from the start in your prepolymer synthesis, so it doesn't matter to wait with the chain extension until you add the water. In the A95 case, you are adding the hydrophilicity at the point when you do the chain extension. So this needs to be done before adding the water, because you need to hydrophilize before you add the water. And this is this chain elongation then causes higher viscosity, and that's the reason why we add some more acetone to get the viscosity under control, and also it controls the heat a little bit better. Yeah.
Okay, great. Thank you so much. Our next question, doesn't the extra acetone affect the overall process time negatively since distillation will take longer?
Okay, sorry. Yes, I mean, we were talking about improvement of the process time, and now you add the additional acetone. Yes, of course, you need to evaporate more acetone. Yes, that's true. That takes a little longer, I would say. Even the amount is way higher. So I would say in terms of time, it doesn't make a big difference, right? Because as we all know from the evaporation, if you do a batch evaporation, the last couple of percent take 80% of the time, right? So the first big portions, that goes off easy. And then really reducing the last 1, 2, 3% of your acetone, that will take the longest time. So it really doesn't matter so much where you start from time-wise. Energy-wise, you're right. Energy-wise, this needs to be taken into account, that you have to evaporate more acetone.
Okay, great. Our next question, are there any means of improving the water resistance?
Yeah, interesting question. I mean, just from the chemical properties, it can be, I mean, it can be easily explained why we have this lower water resistance. When we go back to the chemical structure, if you go to the, where's my DMPA? When I have the DMPA, the hydrophilicity of the acid is relatively low. That means when I only at the point when I add the amine, which is then causing my acid to turn into a salt, that causes the real hydrophilicity, right? So the salt is the big hydrophilic or the hydrophilic component. The effect is that in classical DMPA-based PUDs, often the TEA, the amine, is then later on evaporated from the PUD and it is released. Then you go back to the DMPA. So it is then back to this original acid state and it is less hydrophilic again. So that means less hydrophilic after the application is an advantage, because then it doesn't, the water is not affecting the problem or the product so much. In the A95 case, we already, in case of the A95, we always start with the salt, and the salt stays in the system, so the hydrophilicity stays. And this is the reason why we have less water stability. In the examples I showed, we always went for a very high amount of A95. So that means we aimed for the highest solid content, right? So we took the highest hydrophilicity possible to really optimize for high solid contents. If you don't do that, and if you exchange part of your A95 and you're fine with the solid content of your existing system, and you just use it for the reasons of a simple process and more design freedom with other building blocks, and you exchange part of this with classical amines to do the chain extension, then you also get way better and comparable water resistance than with the DMPA system.
Okay, our next question. Can you suggest a PUD dispersion for floor coatings to avoid hot tire marks and superior abrasion resistance?
Okay. Actually, a very short answer, no, I can't. So as I stated in the beginning, we are specialized in making building blocks, making raw materials for PUDs. We are not making PUDs. I mean, what I present today is examples from the lab to test or to make suggestions to our customers for their own PUD systems. We are not offering any PUDs ourselves. So this is something where I've only limited experience in, well, suggesting or recommending a certain type.
Okay, our next question. How are PUD dispersions cured with waterborne isocyanates?
I'm not sure if I get this completely correct. So there are means, of course, to have kind of a post cure of a PUD. So the PUD is typically not cured, right? At all. As I said, we have this the thermoplastic chains. You can, of course, add some waterborne isocyanates. I think this goes into the direction of waterborne isocyanate trimers, which are then truly crosslinkers. So there are some trimers that are waterborne, or at least hydrophilic isocyanate trimers are available in the market. We also have some formulations available, or guiding formulations for this application, which is now not necessarily closely related to the A95 or the DMPA, works for both systems. I can give some. I would have to come back to this via email, I guess, that I can make some more recommendations how to really cure this with an hydrophilic polyisocyanate.
Okay, great. Our next question. Can you give some information on self-cross-linking PUD based on an A95 chemistry?
So here I have to think a little longer. So self-crosslinking in this case would mean that I probably have I take advantage of the of the competing reaction, right? That my water attacks my isocyanates and of my prepolymers. That means that they are then, if I really do it in a controlled way, they are turned into amine and then react again. So the amine, so the decomposed isocyanate is turned into the amine, and the amine then reacts with another isocyanate to really do this, kind of using a mechanism of a moisture cure, if you wish. This can be done with PUDs also, but again, this is not affected by the kind of emulsifier you use. I would say I don't see a big effect of the emulsifier in this case. Works with both DMPA and A95.
Okay, our next question. Is this suitable as a chain extender in aromatic isocyanate-based PUD?
So, as we saw in the overview of the applications, right? So aromatic versus aliphatic isocyanate-based systems aromatic systems are gaining more and more importance, especially if you do not want to use it as a coating system, right? For systems that are not visible anymore later on, that could be an adhesive, that could be a base layer of an artificial leather, where you're not relying on the light stability. So we see a lot of aromatic systems, aromatic isocyanates coming up also in the PUD world. Generally, as as Evonik Crosslinkers is not offering aromatic isocyanates, we have limited experience with this. I don't have any guiding formulations, for instance, but I don't see any reason why it should not work with A95. So it should also work in this case. I mean, the general effect is you will have, that with aromatic isocyanates, you will have more difficult to control pre-polymer synthesis because they are not as selective as IPDI is. So this 2-to-1 ideal we saw in the pictures is less easy to achieve with aromatic systems because they're not selective, and this is then even stressed by the fact that aromatic isocyanates are more reactive, so your pre-polymer synthesis will be faster. Faster usually means less selective, but other than that, I don't see any reason why not to use A95 also in aromatic systems. So the effects that you don't have to dissolve your DMPA, all this stuff that counts for making an aliphatic isocyanate-based PUD synthesis easier, also should make the synthesis of an aromatic isocyanate-based PUD easier.
Okay, our next question. How much VESTAMIN A95 should be used?
That's a good question. I mean, as I showed in the tables, in order to achieve the highest solid content, you should put as much A95 in your formulation as possible. As much as possible means in this case just a stoichiometric amount, right? So you have we always use, in our cases, we always use exactly 1-to-1 stoichiometry of NCO to amine. And so the amine in this case is the A95, the chain extender. And you want to choose exactly 1-to-1 stoichiometric ratio to the amount of NCO you have in your prepolymer. This is the case if you go for the highest solid content. If you want to have a more balanced profile and you want to also look at the water stability, for instance, you can go down to, I would say, a typical ratio would be somewhere, if you compare A95 to then, for instance, EDA, the ethylene diamine you use as a additional chain extender, I would say, 50-50 also works fine. Less would become difficult for, then you would go down so much in solid content that it doesn't make sense anymore. So anything between 50-50 mix with EDA and full 100% stoichiometry compared to the NCO works.
Okay, our next question. Does A95 substitute totally DMPA?
I know of people who combine both, but I would say in 95% of the cases I'm aware of, yes, it does. In the applications where A95 is used, maybe that's the reason why it's called an A95. No, sorry, just joking. No, in 95% of the cases, yes, it totally substitutes DMPA. If it's suitable for your application and you do not have to rely on, let's say, the water stability, as we pointed out, it is usually appropriate to exchange the DMPA completely.
All right, our next question. Are the chain extenders that have a pendant sulfonate groups as opposed to being placed at the end of the extender? Also, will the sulfonate groups interfere with any hydrogen bonding between the amino groups to give hydrogen bonding crosslink?
On the first question, so can you place the sulfonate group other than on the end that have, I would say if you screen chemical libraries, I'm sure you will find such a molecule, but I'm not aware that anything is available on a, let's say, commercial level in this case. Will the sulfonate groups interfere with any hydrogen bonding? Usually I'm just aware, I mean, normally you have the hydrogen bonding between the urethane groups, not so much, the amino, the amino groups before they are built into the network. No, we don't know. I don't see any interference here with the amines and the sulfonate groups, no. There are many questions. I like that.
Yes, we have quite a lot of questions today. So our next question, Are there any issues trying to react both the primary amine and the secondary amine of the A95 into the backbone of the resin?
No, no, there are not. I mean, of course, yes, you will probably, if you do, let's say, a decent, let's say, kinetic investigation, you will see that the secondary amine of the A95 is a little less reactive than the primary amine. When you compare that with the EDA, which only has primary amine groups, that in theory should react faster. I agree. But let's say in a practical experience, you won't, the amines react so fast with the isocyanate, you won't see a downside in your synthesis time or in your reactivity, or even in loss of isocyanate to the water, right? This is also a concern maybe you might have, but this is nothing of really, nothing of concern, no problem.
Okay, our next question. Is it possible to formulate PUD from aromatic diisocyanate, for example, TDI, using A95?
I think this is a double question. We had that before, right? Yeah, yes, you can make aromatic PUDs using A95. Short, in short, as I said before, in the longer version in the questions a couple minutes ago.
Okay, our next question. In your sample recipe, it looks like the VESTAMIN A95 is added after the dispersing step. Is that correct?
Oh, does it? Then it's a mistake. No. You have to do the chain extension in. Let's go back here. So either this is the complete list of steps, right? So you do first the pre-polymer synthesis, then you do the chain extension with A95, and then you have the dispersion, the addition of water. Also in this picture here, where I have it, so you do the pre-polymer synthesis, add the A95 as emulsifier, chain extender, then you add the water.
Okay, our next question. Is there any significant color development in the film in the A95 system versus DMPA?
No. Both systems are perfectly fine for high quality coatings, no coloration, nothing, no clear coat quality. I would say no differences. I mean, of course, you have to look after all the other ingredients as well, of course, right? So we just had the discussion between aromatic, aliphatic, but the A95 doesn't change anything to the system versus DMPA.
Okay, our next question. Should the pH be controlled with the addition of A95 upon water dilution?
No, actually, it's much less of a problem, right? I mean, with the DMPA, you have to neutralize it carefully with the TEA to form this salt and get rid of the whole acidity. But with the A95, you already start with a neutral salt. As we just put here in this picture, you end up with a pH somewhere between 6 and 7 automatically, without any other means of neutralizing or controlling pH.
Okay, next question. Do you have any comparison data of the shelf stability of PUD from DMPA and the VESTAMIN 95, such as low temperature storage?
Actually, I'm not. I mean, I would have to. This is, I think, the first time I really need to ask my colleague Dennis, who would originally give the presentation. I don't know if we have much data on low temperature storage. What I know is that we typically test all of our formulations I show here at elevated temperature. So we store them 8 weeks at 50 degrees C in order to see if the dispersion stays stable. And yeah, if they would not survive this, I would not present it to you. So on the high temperature side, we tested. I'm sure, I don't know for the low temperature, but yeah, no issues to be observed so far.
Okay, and this is going to be our last question of today. Can you use A95 in a conventional pre-polymer dispersion process into the water instead of using the acetone process?
So that means what is the conventional prepolymer dispersion? So that means you would take a high boiling water, a hydrophilic solvent. I'm just thinking of reasons why it should not work, to be honest. I'm just not aware that anybody who is already using A95 today does it. So all customers I know of that are using A95 as of today are using it in an acetone process. I'm not aware that anybody does this, but I cannot think of a reason why it's not working.
Okay, thank you so much. And thank you everyone for attending today's webinar. Just as a reminder, we will send you a link to the recording of today's event so you can watch it at any time and share it with others at your company. We will also follow up to any questions we weren't able to get to today. Thank you again for attending and have a great rest of your day.